Hello, everybody, and welcome to today's webinar presentation, Scaling Prometheus Metrics and Kubernetes with Telegraf, brought to you by InfluxData. I would like to introduce you to our presenter, Chris Goller. As an architect with 20 years of experience, Chris brings tremendous energy, expertise to InfluxData. In particular, Chris likes to try out using new technologies and sharing his learnings with the staff at InfluxData, as well as with the community. So with that, I'm going to turn things over to you to begin the presentation.
Okay, great. Thank you so much. Yeah, I kind of want to talk a little bit about how at InfluxData we use Prometheus and some of our lessons learned. We have a new product called Influx 2.0, and it's got a free cloud service that allows people to put their time series metrics in. And as we were building it over the course of the last couple of years, we had built it on Kubernetes with many different microservices. Each one of these microservices had many Prometheus metrics. And we ran into numerous problems as we were scaling it out. And many of these mistakes are my own. And I kind of want to take you through the stories of a few of the mistakes that we've made over time and how we were able to use Telegraf to kind of get past some of these scaling issues. And near the end of the talk, I'll talk a little bit more about some of the general architectural ideas about how we ended up making some of these things more of a scalable, resilient solution for Prometheus. Okay. So the first curious case of the missing metrics. This was something that I'm just going to spoil the ending. It was one I made, put too many labels into my Prometheus metrics. And once you have metrics into your program, it's so addictive to try to understand more about what your program is doing. And the punchline here is I added just one too many, which really increased the cardinality of Prometheus significantly. But what we're going to do is talk a little bit about not how the end conclusion, because the end conclusion will seem easy. It's like, oh, you shouldn't have done that. But in many cases with software, it's better to actually investigate why and if there are ways to put guardrails on and what we could have done to prevent these problems without shooting ourselves in the foot with Prometheus. So to set the stage about the missing metrics, we're using Kubernetes, and we've put all of our microservices in Kubernetes. We've got every one of our microservices exposes Prometheus metrics. One microservice is called Gateway, and Gateway is the gateway for all API requests, including all, say, user authorization, dashboarding, running of queries, and writing data. And the other suspect is QueryD. So QueryD is essentially a microservice daemon that runs our Flux query engine. Each one of these has exposed Prometheus metrics, and we have many of them. I'll go into a little more detail about how they are structured and what the communication paths are in a moment, but what are the suspects we have here when we were missing metrics? Was it Prometheus as the one missing metrics? Are we missing scrapes? Is Kubernetes hiding something from us? Did we lose some pods that we didn't know why? Is Gateway not producing the metrics it should? Is QueryD not producing the metrics it should? The case was all about why is it that we're not able to understand what's happening in our own system during our beta process. So Prometheus, just briefly, Prometheus is a way of taking a microservice and instrumenting it with an endpoint. So Prometheus is, you could imagine that it was kind of like a watered down version of SNMP, where you only you have an endpoint that is full of metrics that can be produced by the application itself. Its symbol is this torch, the Prometheus torch, as in the mythology. Our Go microservice implements this Prometheus endpoint, and attaches different kinds of metrics that we're interested in to this Prometheus endpoint, which is exposed in the case of gateway, our gateway microservice over port 9999 at the metrics endpoint. So as a developer, you end up adding in more and more metrics to various types of things in your gateway. For example, you may want to instrument how long it takes for an HTTP call to start and stop. Perhaps you want to instrument how the duration it takes for the API to call some backing data store. And this is the kind of data that the metrics endpoint can show up. So in this case, I'm displaying some of the Go microservice internal metrics. These are garbage collector duration. So on general, a summary with quantiles, the 25th percent quantile, 50th, 75th, and 100, for example, like how long it takes in seconds to run the garbage collector. The number of Go routines. In Go, a Go routine is kind of like a green thread, in quotes. And so this, in Gateway, for example, it apparently at this point it has 252 Go routines running. And at the time that I took this snapshot of the metrics, we were building on 112.10. So it gives a bunch of information about it, but I want to show you a little bit about types. So there's summaries, which can be in quantiles. There's gauges. A gauge in Prometheus is just like it is in SNMP from the 80s, where it is strictly a number that can be changed to any kind of value. The version itself is also a gauge, so it turns out to be a string. And you can see this is kind of an interesting pattern in Prometheus. You're allowed only a single value for a specific label set. So Go info has a label set of version with this particular version, and it's allowed one value. So in order to add more descriptions to a particular metric, you would have to add in more labels. Okay, so this one right here is actually another gauge. How many bytes have we allocated? And finally, this is a counter, which is the total number of bytes ever allocated, on this process over the course of it running for weeks on end. And that's a counter, and counters are increasing only. They can only increase. Prometheus metrics are the values of Prometheus metrics are always considered floating point numbers internally. Okay. So the way it works with Prometheus, Prometheus itself goes and discovers where all the Kubernetes microservices are that can that produce metrics. And this is an example of a Prometheus server configuration that's saying for every 15 seconds, use Kubernetes Service Discovery, that stands for SD, Service Discovery, and look for all services and scrape their metrics every 15 seconds. The interesting thing about that is as you want to add in more microservices, a service discovery is able to find them on basically every so often. It's able to like refresh the Kubernetes discovery and find out where the other microservices live. So it's kind of a nice pattern there. But okay, so I'm starting to talk a little bit about Kubernetes. So let's Kubernetes is always described in various kinds of patterns and drawings like these, and I've picked several of them off the internet that I think are really interesting and beautiful. But the point about Kubernetes is it's a control loop that allows you to state what you wish the world to be, and it goes about trying to turn on or off processes. Now, those are called pods. And Kubernetes, the most atomic unit of a specific of Kubernetes is a pod. A pod is something that has more than one container, and as this drawing shows, it's kind of like this pod has 3 containers. Containers are like either Docker containers or other things that implement the container runtime. And these are essentially generally single processes that are running. So in this particular pod, there are 3 processes running, and they all share the same IP address, and they're able to be accessed by each other over localhost. So you could almost imagine it as like your own little virtual world here for these processes. Now, one of the other nice things that Kubernetes does is when you state, hey, my deployment, I want to have 4 of these replicas. So you have a template that you specify, this is my pod template, and I want 4 of them, and it tries to produce 4 identical pods. And that's where Kubernetes gets its a couple of nice features, namely it's auto scaling, or it's scaling, so you can state, hey, I want 4 or 100 or 400 of these particular pods. And also the networking is fairly straightforward too. So if you put a service in front of this deployment, service can round robin across these pods, if you should so please. But with Kubernetes, there's a great deal of complexity because it has a great deal of power. Kubernetes architecture is still something that I think everybody is evolving as it's going forward as a community. How you go and establish good architectural patterns on top of Kubernetes is something that we're all trying to understand right now. And these diagrams are really just kind of like the most basic understanding of how things can work and some of the terminology therein. But what I want to show is talk a little bit about how we set up our patterns. I just want to mention one more thing from my slide notes. One interesting thing about all pods is that pods can have resource limits. So you could say, hey, this particular pod number 4, I want it to only have, say, 1 GB of memory ever. That's it. And you can also specify the amount of CPU. So it gives a way of isolating resources across a cluster. Okay. So how does Influx Cloud work? This is our service that we just put out into GA about a month and a half ago. What I'm trying to show here is we have a Kubernetes ingress, and traffic from the outside world comes into these ingress, and it is round robin across our gateways. Gateway, again, is our API tier. So data for writing comes in, queries come in for our Influx database, our time series database. And they're round robin across. Now, the triple dot is supposed to stand for, like, we have potentially many of these gateways. And we generally run on our service now between 100 and 200 of these gateway pods. So there's 100 or 200 right now of these processes running to handle all the inbound traffic. The gateway tier, when a query comes through the ingress point, it also round robins across a scalable deployment of query D. Query D is the query engine that we've built to be horizontally scalable. So as more queries can come in through this, we have the possibility of adding more and more query nodes. And I think I'm trying to remember how many we have right now, but it's between 50 and 100, I believe, of these particular processes. So ingress, the traffic comes into the ingress, it is round robin across the gateways, and gateways round robin across this tier of query Ds. And these are elastic. Each one of these, every single one of these gray boxes has Prometheus metrics. And so our scraper is responsible for scraping all the metrics across all of these. So that's actually potentially a problem, because with missing metrics, if you're like, why is it that gateway claims that it serviced 10 requests, but query D says that it has serviced 100 requests? Where is the missing data? Where could that possibly be? Which leads us really to the first problem. Really, debugging Prometheus is really quite hard. You can look at the Prometheus database itself, and it has its own metrics around what it was trying to do when it was scraping. So here, these are the metrics that would be on Prometheus while you're scraping, say, our 2.0 product. And it really comes down to having very little, in that it says it's the amount of time it takes to scrape all of the services. And as this metric goes up and up, in terms of time, you're finding out that you're falling further and further behind with your Prometheus metrics, or Prometheus scraping. So a single Prometheus server is responsible for, in this particular case, would be responsible for scraping hundreds of processes in 15 seconds. Well, to put out what's going to happen if each one of these processes has megabytes and megabytes and megabytes of metrics data. That can be extremely heavy on the load for Prometheus. But the problem here is you don't really know who is at fault. You know it's taking longer, but you're not really sure who's doing this. So how would we isolate some of these things? Well, if your Prometheus instance is falling further and further behind, what you do is you can turn on more than one. It's basically scalable in one sense that that each Prometheus is now responsible for scraping a certain subset of the services. So my example here is we have two Prometheus now, and Prometheus on the left is scraping a specific Kubernetes namespace A, and the Prometheus on the right is scraping a second namespace B. So already as an operational sense, we actually have to encode quite a little bit of operational knowledge in each Prometheus implementation or each Prometheus deployment. Because now you have to be able to refactor your entire Kubernetes network space into different namespaces so that you're able to partition up the Prometheus scraping. The hope is that with this centralized Prometheus scraper, that you're able to decrease the load on each one of them so that a particular Prometheus scraper is able to just scrape, say, namespace A in the allotted time in 15 seconds. And you hope that the one on the right is able to scrape the namespace on B. But again, it requires quite a little bit of operational configuration. So it allows you to have this kind of granularity. But it really doesn't help that rogue developer, me, who adds in too much data in one specific pod. So this manual distribution into these federated Prometheus, it ends up becoming a problem because scraping failures are inevitable. And how can we, like, thinking architecturally for a moment, how do we completely avoid saturation of this scraping? If now that we have two, if Prometheus the Prometheus that's handling namespace A is unable to finish its scrape in 15 seconds, now what? Is it possible for us to break that down into even more granular components? And it is up to a point with the service discovery. Service discovery says, hey, I really want to just look at namespace A, but maybe I want to do just a single deployment and so on and so forth. So it's possible to go smaller and smaller units, but eventually it runs out. Eventually a centralized scraper, it still has to scrape potentially too many items. So centralized scraping really means that the developers need to know nothing because they're taken care of by the infrastructure, but then the operators need to know everything. What do we need to do to split the load? So what I'm trying to point out is that service discovery can lead to really significant scaling problems because the only scaling strategy is to discover smaller and smaller Kubernetes types. But I want to point out, at what point is this really no longer discovery? So which we came to the way we ended up doing, this is step one on what we ended up trying to do. So what we did after we figured out that there was some of the saturation with missing metrics, with saturating scraping, we tried to isolate each microservice with what's called a Telegraf Sidecar. A Telegraf Sidecar is this notion that you can place Telegraf, which is our collection agent, next to the process by putting two containers in a single pod. So this particular shape here is to kind of denote a single pod. And this could be our application, a Go application. And we have Telegraf that sits inside that application and scrapes metrics locally. So how do we get around this notion of service discovery does not scale? Well, don't use service discovery. The simple answer is you place a second Prometheus scraper, a Prometheus scraper inside every single one of your pods. That's to monitor another process with Prometheus metrics. This way, the developer now has to handle the scaling problem, because now you have extreme granularity of scraping. The configuration is no longer shared, so it's no longer a burden on your operation team. And so why should it be shared? Each individual scraper can have its own unique scraping rules. And this really fits better the Kubernetes model, where you're isolating components so that the brains of the component are as local as possible to the program at hand. So we're going to talk a little bit more about how it's done. Here's an example deployment of Gateway. So Gateway, we'll have 100 replicas, and we can state 2 containers are within the pod template. One container is Telegraf and the other is Gateway. And now Telegraf can be configured to scrape the Prometheus metrics of Gateway over localhost. And it forwards on the metrics to InfluxDB. And it can forward it on, in this example, to our cloud instance. It's always really good to monitor the monitoring system. You always need to know some sort of meta information if you're collecting metrics in the correct way. It's not good enough to just say you're collecting metrics. You really have to instrument the metrics collection process in order to make sure that you have the data that you really need when you need it. So with Telegraf, you can have multiple inputs and multiple outputs. But really the problem here is, with the solution, how do we determine if you're scraping correctly? Telegraf has this wonderful input called Influx Internal, and it provides that additional metadata, how well the scraping is performing and how well it's able to send the metrics on to another agent. So this external monitoring system not only collects the Prometheus metrics, but it also can collect this inputs internal data, and we can get a more holistic sense of which of these processes is the one overwhelming the metrics collector itself. So in a graph, what did we see? When we started instrumenting all of our processes with this Telegraf Sidecar, and then we turned on this internal metrics, we saw on a deployment, which is on the left, we saw the metrics collection kind of flatline, and for the orange, which means it doesn't have an increased cardinality as more and more metrics are added over the lifetime of a program. But the real smoking gun is this curve, this blue curve. What this is showing us is the amount of metrics that are added to Prometheus over time increases. As the process lives, it gathers more metrics. As the process continues to live, it adds even more metrics, and so on and so on and so forth, until some sort of saturation event. Well, it turned out that here's an example of the kinds of requests or the kind of data that we were using. I wanted to collect the API request in duration, like how for each type of API request, say for example the query, I really want to know how long it takes. And we put in our handler is Gateway. We put in another descriptor that we wish to know what kind of method it is. Is it get, is it post, so on and so forth. We were interested in what path. Is it the query path? Is it the write path? We were interested in like the status code, and so in this case, it's some sort of unauthorized. And here's where the problem occurs. I wanted to add in the user agent. I thought it would be really interesting to be able to compare and contrast what user agents are sending these web requests to our gateway. Well, this particular field is descriptive of the data at hand, but it's a completely free form. So you can have as many of these kinds of user agents as possible. As you turn on Gateway, more and more of these different kinds of user agents come in, and we have like an unbounded cardinality. So really, the number of cardinality is the handler times the method times the path times the status times the user agent. Because it turns out path and user agent are unbounded, we ran into enormous cardinality. Enormous cardinality, tons more metrics. Tons more metrics means that the scraping falls over. In this case, because we isolated the Telegraf Sidecar right next to the process, the scraper that falls over is only that one, that is right next to the process at hand, rather than a centralized scraper. If a centralized scraper falls over and is not able to accomplish its job, it affects all systems. An isolated Telegraf Sidecar affects only a single system. More labels mean more cardinality, but I don't think this is a case of you're doing it wrong. Well, I did. We're doing it wrong because it's had a lot of extra cardinality in the Prometheus method. But labels are really meant to identify a particular kind of metric. But user agent is not identity. It's not the identity of a metric, but it's an additional context that I wish to kind of note about some of these things. In the Prometheus style of metrics, you're not really allowed to add more context except for increasing your cardinality in some way by adding labels. Well, what if we, instead of extending the telemetry to capture user agent information, what can we do? Where was this put into place? Well, it was here. Here's the little piece of code, and we started adding in user agent. Once we found that we had this increase, we could, using the Telegraf's debugging information, we could go back and look, why do we have these extra labels? Ah, yes, because the user agent was added. The problem is that Prometheus really only has that one and only one value. It's unfortunate that it's only one way of adding in more information. What Prometheus allows you to do, though, is if you want on server side, you can say, hey, I want to take that user agent and I want to drop it. Unfortunately, by that point, you've already scraped hundreds and hundreds of megabytes of metrics, and you fall further and further behind as a centralized scraper. But with Telegraf in place, we have a different option. What we can do with Telegraf, we can scrape the metrics locally. This is the Telegraf configuration. And we can say, hey, look, let's take that specific tag and convert it to a field. In the InfluxDB metrics, you're allowed to have more than one kind of piece of context that is not going to increase your cardinality significantly by using fields. So we change to a secondary field, but we don't pay this penalty of many unbounded sets of cardinality by converting a tag to a field. So for a specific developer, you're able to put the context, the specific way of pulling in metrics right next to the process at hand, rather than having a centralized configuration that must satisfy everyone. It's significant CPU and memory load potentially, doing this, but it's only one single developer's microservice rather than impacting them all. So it allows us to ultimately retain the context, but have no cardinality impact, or very little cardinality impact. But is there a way to kind of prevent this from really happening? I mean, really, we want to allow the developers to express their metrics. And in Prometheus, there's really no real way of preferentially preserving metrics. But we really want to provide developers like a safe experience. So Telegraf, as long as you put it right next to the container at hand, has this other thing where you can limit the number of tags that can come back from Prometheus. In this case, we're putting in we're saying, hey, we're just going to put guardrails around it just in case developers add in too many of these kind of limits. We can limit the number of tags for specific metrics to 3. And the ones we wish to keep are going to be handler, method, and status. So this is a runtime solution. So now we have no need to recompile. And again, this configuration is completely under the developer's control without any need for the operations team to constantly be updating the centralized Prometheus configuration. Once we fell into this strategy of, okay, we can put the Telegraf scraping of Prometheus metrics right next to the process at hand, that allowed us to rethink a lot of the centralized configuration. For example, in Prometheus, if you wish to put password control so that you're not necessarily exposing your metrics to everyone, you have to put the bearer token or username and password, there's settings for that, in a centralized configuration, such that that the operations team really has to handle updating and rotating those passwords or tokens, which works. But again, we're looking for heroic operations people to constantly be updating things on a developer's time schedule, a very interrupt-driven workflow. I mean, the centralized configuration really requires this distribution of passwords, but that also means that when the central server and scraper needs to be restarted at the same time as all pods when that password is changed. Okay, so instead, let's decentralize. Let's use the Kubernetes, the standard Kubernetes way, decentralize and put the credentials shared in the pod between the service and Telegraf. And this is how you would do that. So again, within using our microservice with Telegraf right next to it, we can state, hey, we just want to use this particular bearer token, Hunter2. And that allows the developer to change or rotate the token for their particular microservice and the one at Telegraf at the same time, because both of them are in a single pod, both processes that are in a single pod, and a single pod restart would rotate both of these credentials at the same time. There would be no need to have some sort of coordination, some sort of large-scale coordination between a centralized service and the distributed one. So it's just another kind of thing that allowed us to decentralize the Prometheus scraping and kind of opening up the door to much more customized, more rigorous architecture. So I think really what I want to point out is that scaling is not just more manual processes. Adding more configuration to a centralized Prometheus and more coordination between teams is not the same thing as just saying that you can do it. Yes, of course, you can turn on more and more centralized servers, but the administrative burden, that's where there's a problem. Usually when you see people like me that made those kinds of mistakes where we've overwhelmed a centralized scraper, the advice is, well, you're doing it wrong. And sure, that's true, but really that is not the same thing as scaling. Scaling is really the ability to empower developers, and scaling is also being able to predict failure modes. And predicting these failure modes for metrics, in this case, is overwhelming the scraping for Prometheus. And with that prediction at hand, we can decentralize scraping to be very local. That really allows us to kind of have these additional follow-on benefits, such as rotating keys and more personalized scraping for the developer. Okay, briefly, watching the watchers. So this is another kind of issue that we ended up having sometime last year, and we missed some solid alerting. We were wondering why is it that when we're scraping we're not getting all the pods, and how do I check that a centralized scraper is getting is actually able to scrape all the pods? Well, in Prometheus, again, there's really, with a centralized scraper, it's very difficult to know if Prometheus has received all of the metrics. And in fact, it's really hard to know if Prometheus itself is alive unless you have another service, watching the watchers. Telegraf can be set as a Kubernetes watcher as well. Once Telegraf is in kind of the system, it has so many different kinds of inputs. It doesn't have to be just Prometheus. You could potentially be running a different set of Telegrafs that also can read the Kubernetes Inventory. The Kubernetes Inventory is a plugin that allows Telegraf to produce metrics about the number of pods that should be used or should be on for a deployment or a stateful set, and so on and so forth. Additionally, the Telegraf can provide metrics about itself. That's where we are this internal again, and this is really the key. The internal metrics and the Kubernetes inventory can be output to Influx, or it can be output to Prometheus, and so on and so forth. There's many, many kinds of outputs for Telegraf. It's like universal metrics translator. But one of the things that I want to point out is that this external Influx DB v2, this is our cloud offering. It allows us to take some of the metrics that are about our Telegraf and send them to a secondary, different monitoring solution. That way we have some notion we can check between these two. if there's a difference, then we have some idea that it is one or the other that is having problems. So with the Telegraf Kubernetes inventory, we're allowed to say, hey, like, look, how many for a specific Telegraf image, how many of them are being there? So there's supposed to be 96 of these containers, but there were only 30 being gathered. So right there is, again, our smoking gun about how one can use this Telegraf system and have internal metrics that are not really provided with the Prometheus scraper to allow us understanding or kind of this meta information about our metrics. How many should we be gathering? We should be gathering 96. So now we can go and dive in and find out where are our metrics not being gathered. Just another kind of way of decentralizing the responsibilities into other types of processes. I want to go through a couple of Prometheus scraping designs. We iterated on this in a few different ways. So what we tried is we had our telegraphs isolated next to our Go microservices that were scraping them and then sending it to a centralized InfluxDB, a single instance, and that works. That works great. Influx is extremely high performance, and so as it's scraping the metrics on this side, all the telegraphs can be configured to push to a single InfluxDB. And that's our open source product, and anybody can use it. It's totally fine. At some point, even that becomes overwhelmed, and so we started using our Influx Enterprise. Influx Enterprise allows you to have a scalable data plane. You could have many Influx Data Enterprise nodes, and Telegraf would send all these telegraphs would send their metrics to a load balancer, and that load balancer would round robin send that to one of these data nodes. So from Telegraf's perspective, it's just sending to a specific DNS entry, and these highly available clustered solutions can handle all those metrics in a very nice way. That way it means we really have an API, right, between Telegraf and these the data plane, the backing data plane, without either Telegraf or the data plane having to know the number of them between each other. Decoupling the solutions. One of the other things that we tried out in different ways, or we've seen customers try, is that these telegraphs can send up metrics into a queue or into a log like Kafka. And this is kind of a really interesting approach because it gives some durability to those metrics. And we have another telegraph that reads from a Kafka topic and then, of course, sends on to the Influx Enterprise. This gives some durability to the entire metrics pathway. That allows Telegraf itself, if it ever becomes overwhelmed with the amount of metrics it's sending, it has the ability to retry, but at some point it could actually crash if it's using too much memory. Again, in Kubernetes, every pod is allocated a certain amount of RAM. If you use too much of it, you're restarted by Kubernetes. So this gives some durability by putting in Kafka in the middle and allowing Telegraf to read on the outside. And Telegraf's able to act the messages in Kafka so that you have some guarantee that metrics are making it through here. You can instrument the entire process all the way down. I want to get to some core ideas about this talk, which is, you have to when you measure and test metric scaling, like you really have to check if there are missing metrics and why. Essentially, metrics health about your system that describes health. You really want to emphasize decentralizing metrics gathering, and you really want to think of metrics as part of the program itself. When metrics are considered part of the program itself, then you start to build, as developers, ways of creating APIs between these components. And finally, you really want to empower developers. They really know their metrics best. And if you push that idea to the extreme, you give them local tooling. In other words, tooling that is close to their process rather than a centralized tooling. The centralized tooling will be, the master of none. It has the ability to do most things in a mediocre way, but it's not tailored to a specific solution. Allowing developers to tailor their solutions will end up becoming much more scalable. So a couple of first order conclusions. It's really way too easy to shoot yourself in the foot with Prometheus Metrics. And yes, of course, you could say you should have known better, but ultimately, the Prometheus Metrics and the scraping is not easily scalable. You really need too many operation heroes if you're going to scale Prometheus and its scraping. I feel like it's very difficult to express other kind of vital information in Prometheus about your program without an enormous amount of centralized control. And finally, and ultimately, one mistake can really impact everyone. In a Kubernetes system, when it comes to scaling, you really want a mistake to only impact the specific microservice. Maybe some second order, more controversial conclusions. I feel like the Prometheus metric format, maybe it's just really ultimately not descriptive enough. It's really difficult to change those metrics over time. So adding in more labels or adding in completely more and more metrics, or maybe even removing some. I don't feel like the metrics game is really solved yet. A solved problem. I know that Prometheus is working towards a slightly more descriptive format called open telemetry. That would be very interesting. I mean, and some of the lessons from even the old school SNMP could be potentially farmed out and figured out a way to make some of these metrics more and more tailored to the specific microservice at hand. I think that there's just not really one answer to everything. There's no silver bullet, but giving people the flexibility to produce their own metrics and giving them an API such as Telegraf that can take in many different flavors of metrics and then output them in many different ways gives developers a chance to really investigate how metrics should be used in part of their program. Finally, really the future that we're going to attempt to do is put our new query language Flux into Telegraf. So Flux will be a processor in Telegraf, and this will allow us to put our domain-specific language very close to the data that's being scraped. And this allows us to almost put monitoring and alerting, like maybe we want to alert or downsample or do some sort of time metrics processing very close to when we scrape, rather than having it done in a centralized way. Again, it's like this notion of how do we decentralize metrics. We're going to have these Telegraf Flux scripts hosted in InfluxDB. That's really cool because then it allows these essentially like runtime plugins without needing to recompile Telegraf. So imagine downloading this domain-specific language from a central server on startup, and then that specific program can be run. Those programs can be checked into version control and so on, allowing this kind of very rich runtime experience very close to the metrics at hand. But really what we want to do is think more and more carefully about how we use metrics in our own software and how others are using metrics in their software, because we want to attempt to kind of get these much more scalable solutions ultimately. Okay, and with that, thank you so much, and I'm willing to take some questions.
Great, thank you so much, Chris. We do have a few questions that have come in. And audience, if you do have any more questions, please post them into the questions panel. The first question that we have today is InfluxDB available in the AWS Marketplace or a pre-built container image on Docker Hub?
Yeah. So yes, in fact, that's a good question. So InfluxDB is on the AWS Marketplace. In fact, like I kind of mentioned this, we launched our 2.0 platform, our cloud offering, and it's also on the marketplace. And I'll have to, I don't have the URL at the moment, but we do have a sandbox in Docker that you're able to try out. So yeah.
Awesome. The next question that we have is, can you talk a bit about what options there are for acting on metrics? What does the stack do to enable automated alerting and actioning on metrics coming in?
Yeah, so we've got a two-pronged approach to this. The first prong is we have an open source project called Capacitor, and that reads data as it's streaming through, and it has a domain-specific language called TickScript and that allows us to do alerting and data processing. So things like downsampling, things like sending, if this metric is above some number, send a PagerDuty alert or what. But we also have Flux, which is our new language for our 2.0 platform, and it also has alerting and notifications. But it is an embeddable language that we're going to start embedding in other processes as well. So for example, Telegraf, where we're going to be able to put these kinds of processing near the edge of metrics collection.
Great. We do have only one more question left. So again, audience, if you do have any questions, please post them into the questions panel. The last question that we currently have is, which programming languages have been used in the platform's development?
Yeah, so for Influx 1, we use mostly Go, 90% Go. We have our chronograph UI that is written in TypeScript. For our Influx 2.0 platform, again, mostly Go, and the UI is also in TypeScript, but we're also using parts of the Flux engine are being programmed in Rust right now. That gives us kind of a nice safety, and it gives us a good deal of performance.
Perfect. Well, that was the last question that we do have. So Chris, is there anything you would like to add before I close things out?
Yeah, I just am hoping that people will share their experiences and how they've been able to scale metrics. I think it's a game that is not yet finished, and I'm interested in seeing us all come up with different kinds of interesting architectures.
Great. And with that, Chris, I'd like to thank you for a great presentation today. I would also like to thank today's sponsor, InfluxData, for providing the audience with a great webinar presentation. And last, I want to thank the audience for joining us today. We hope you learned something new that will help you further your career. Have a great day, and we'll see you next time.